So we're still in section 5.8. So I'll call it 5.8 part 2. So a couple of things that you may have seen as you work with these, if you look through the book, the information on hyperbolic functions. One, hyperbolic functions aren't periodic like the other trig functions, because like explained, it has to do with the unit hyperbola rather than the unit circle. All of them except the hyperbolic cosine and the hyperbolic secant are one-to-one. So one-to-one functions have inverses. So we're going to talk about their inverses. And if we do, yes? I don't think so. I think the argument for I think the calculator just uses just a real number as an argument. So I don't think it matters. I'll look into that because nobody's asked that before. I think that only has to do with sine, cosine, tangent. I think it only has to do with those. So the ones, hyperbolic cosine, hyperbolic secant, if we restrict the domain, like we do with the trig functions, we can define an inverse function over that restricted domain. If we make them one-to-one on some domain, we can define an inverse function. Now, our hyperbolic functions all involved exponential functions, some combination of exponential functions. So what are we going to expect that the inverse functions involve? Logarithms. So all the inverse functions involve logarithms. So the functions themselves all involve exponential functions. The inverses involve logarithms. So let's define these. I think I got my notes out of order here. There we go. Okay. That looks better. So I'm going to start by just listing the inverse hyperbolic functions. They're also listed in a table in your book on page 392. I just want to list them here in the notes, and then we'll go through one example of how we find these inverse functions. So the inverse hyperbolic functions. All involve exponentials. So the inverse hyperbolic sine is the natural log of x plus the square root of x squared plus 1. And our domain is all real numbers for this. Inverse hyperbolic cosine is a natural log, and it's interesting because they're so similar, but the functions themselves were very similar. X squared minus 1 in the radical this time. And our domain, we need to restrict the domain here from 1 to infinity. So that's our restriction to make sure that we can define an inverse function for the hyperbolic cosine. Inverse hyperbolic tangent is 1/2 the natural log of 1 plus x over 1 minus x. And our domain here is -1 to 1. And our cofunctions, inverse hyperbolic cotangent, again very similar, 1/2 the natural log of x plus 1 over x minus 1. And our domain here is -infinity to -1 union 1 to infinity. So we're excluding everything between -1 and 1. Inverse hyperbolic secant is the natural log, all these natural logs, 1 plus the square root of 1 minus x squared. And this is divided by x. And our domain here is 0 to 1. And finally, the inverse hyperbolic cosecant. A little more complicated, 1 over x plus square root of 1 plus x squared, all over the absolute value of x. And our domain here, -infinity to 0, union 0 to infinity.
Can't be 0.
Can't be 0. We're excluding 0. Because we're dividing here by this absolute value, yes.
When you write the bracket, that means we're including it, right?
The
The one before.
The square bracket is inclusive, and the curved bracket is exclusive.
All right.
So this would be a closed dot, and this would be an open dot. So a lot of what we're doing with the hyperbolic functions is kind of mechanical, kind of here's what they are, here's what they look like. We're not going into a lot of depth. Like I said at the beginning, I just wanted to give you an introduction so that you have seen them, so you have some familiarity with their form, so that when you get to some place where you might actually be applying them a little more, it's not the first time that you've seen them or really done anything with them. So it is, I know it's kind of just kind of a list of here's what they are, here's how you do things with them. That's really kind of my intention with this particular lesson, is just here's a big overview of what hyperbolic functions are. So we proved these, and there's a table and a table in your book on page 392. They also graph these inverse hyperbolic functions on page 393. So you can look at graphs of these inverse functions on page 393. I'm not going to put all the graphs up here, but you can look at those in your book. Now we prove these properties. We come up with these formulas for the inverse functions just by applying the property of inverse functions, just the normal way you would find an inverse function back from algebra. So let's take a look at one of those. We'll just go through one just so you see the procedure. So if we have our f of x, and we start with the definition. So f of x is e to the x minus e to the minus x over 2. So we're going to find the inverse of this function the way we've always found inverse functions. We switch x and y and solve for y. So I'm going to rewrite this to find the inverse. So I'm going to say that x equals e to the y minus e to the minus y over 2. And we have to solve this for y. There's a little trick that we do when we have functions like this to simplify them. Anybody have an idea of what we would do to work on this? because we have this e to the y and e to the minus y.
Or not.
Take the natural log?
Yeah.
We will end up doing that kind of at the end, but we need to solve for y. We need to solve for y, so we'd end up with we'd get the natural log of x, natural log of e to the y, natural log of minus natural log of e to the minus y. So we'd still have a mess. It would be a little messy. What's that? Rewrite e to the negative y. You're on the right track. There's when I taught Algebra 2, there was the trick, and I told the students, never forget this trick. When you see something like this, we're going to multiply both sides by e to the y. So multiply both sides by e to the y. So I get x e to the y equals e to the 2y minus 1 over 2. So this gets rid of that e to the minus y. I multiply both sides by e to the y. E to the y, e to the minus y, multiply, you just get 1. All right, does anybody see where we're going with this now? I love working with these kinds of equations. So I'm going to rewrite this. I'm going to simplify this and rewrite it. I get e to the 2y minus 2x e to the y minus 1 equals 0. So I just simplified and rewrote this. Now what do we do? We were talking about a trig equation the other day, Star, with cosines. And do you remember what we ended up doing there? What if I let u equal e to the y? I rewrite this u squared minus 2x u minus 1 equals 0. And what can I do with this? Quadratic. We could put it in the quadratic formula. So this is quadratic in e to the y. So I have u squared, or e to the y squared, minus 2x e to the y minus 1. So this is quadratic. We can put this in the quadratic formula. And when we put it in the quadratic formula, we end up with, and then when at the end, then we'll take the natural log. We end up with, let me do one more step here. When I put it in the quadratic, u equals 2x plus or minus the square root of 4x squared plus 4 all over 2. And when I simplify this, I get x plus or minus the square root of x squared plus 1. I can factor out a 4 here, take the square root, I get a 2, so the 2's cancel out. So I get e to the y, finally, equals x plus or minus the square root of x squared plus 1. So y, finally, equals, we take the natural log now, is the natural log of x plus the square root of x squared plus 1. Why did I choose that only the positive there rather than the negative? Can't take the natural log of the negative number. So if I subtract x squared plus 1, square root of x squared plus 1 is going to be bigger than x. And if I subtract that, I get a negative number. So I can't have a negative number as the argument for the natural log function. So that's the derivation of the very first rule for the inverse hyperbolic sign. And the others are very similar. And from looking back at these equations, this one, these, you can see that the work might be a little more involved. These two are pretty straightforward. Some of these just the algebra in doing it, finding the inverse can get pretty messy, but it follows along these same routes. But this little trick of multiplying through by e to the y when we have a combination like this, that's a really good one to remember for simplifying things. And then also this picking out that this is a quadratic equation. All right, questions on that? So we can use our definitions now, the definitions we came up with for our functions to come up with differentiation and integration formulas. So we're just going to differentiate each of these to come up with the derivatives of the inverse hyperbolic functions, and then from our derivative equations we can come up with integration formulas. So I'm just going to list our derivatives and our integrals. Don't memorize these. The main thing that I want you to get out of this is to see the forms of these functions, and especially when we're talking about the derivatives and the integrals, to see that they're similar to the trig functions. So if you get to a integral and you say this looks like an inverse cosine but it's not quite, that should turn on a little light that says maybe this is an inverse hyperbolic function. So you have that little bit of familiarity. So that's really what I want you guys to get out of this part of the lesson. So our formulas: differentiation and integration. And I know that there are homework problems later on in the semester and later on in the year where I always get questions. I got to here and I wasn't sure what to do, and it turns out that it's an inverse hyperbolic function or a hyperbolic function. So just to get that little bit of awareness. So in all of these, we're saying that u is some function of x, just like we always do with our differentiation and integration formula. So I'm going to use a u just to make it a little more general. So u is a function of x. So our derivative of the inverse hyperbolic sine of u is u prime over the square root of u squared plus 1. The derivative of the inverse hyperbolic cosine is u prime over the square root of u squared minus 1. So if you look at your formulas for sine and cosine, inverse sine and inverse cosine, these are very similar, again, often up to just a sign change. So the derivative of inverse hyperbolic tangent is u prime over 1 minus u squared. Does anyone remember what the derivative of the inverse tangent is?
1 over 1 plus x squared.
1 over 1 plus x squared, or u prime over 1 plus u squared. So very similar up to a sign change. So if you see something, this is what I was pointing out a little earlier. Something that looks kind of familiar, but not quite. Think, and I forgot my h here. Think hyperbolic trig functions. Looks like inverse tangent, but it's not quite. Yeah.
When you write u prime, do you mean is that just the u in the equation, or what is u prime?
So u is some function of x. So if u was like,
It's the
u is like 3x plus 1. And then, so this is just the derivative of u and then whatever u is. It's making it a little more general rather than just x. All right. We'll do our co-functions, derivative of the inverse hyperbolic secant of u is minus u prime over u over the square root of 1 minus u squared. The derivative of our inverse hyperbolic cosecant is minus u prime over the absolute value of u square root of 1 plus u squared and finally our derivative of our inverse hyperbolic cotangent u prime over 1 minus u squared. I think I have a sign wrong here. I think it should be minus. Let me double check on that. It's not negative?
Yeah.
So these are both the same. Okay. So I was right. So I thought it should be minus. I'm thinking regular trig functions. So hyperbolic trig functions can be tricky. All right, and we use these formulas to come up with our integration formulas. So you notice that each of these is the cofunction, or the sine and cosine are the same up to a sign change. The secant, inverse hyperbolic secant, inverse hyperbolic cosecant, the same up to a sign change. The inverse hyperbolic tangent, inverse hyperbolic cotangent are the same. So we really only have 3 integration formulas for our inverse hyperbolic functions. And I'm going to put the integration formulas in logarithmic form rather than in this form. I'll write them in logarithmic form because usually that's what you're going to come up with. So our integration formulas. The integral of du over the square root of u squared plus or minus a squared is the natural log of u plus the square root of u squared plus or minus a squared plus c. And the positive gives us the inverse hyperbolic sine, and the negative is inverse hyperbolic cosine. Our second integration formula, du over a squared minus u squared. 1 over 2a, natural log a plus u, a minus u, plus c. And, oh yes, du, thank you. And this is for inverse hyperbolic tangent or cotangent. And finally, our third integration formula, du over u square root of a squared plus or minus u squared minus 1 over a natural log a plus, this one's pretty messy, and a plus c. And the minus is for inverse hyperbolic secant u, and the plus gives us inverse hyperbolic cosecant. A is just a constant. So those are our three integration formulas. So again, what I'm hoping for here is after today, after doing a little practice with these, when you see some kind of expression that looks similar to maybe a trig sub, but doesn't come out, isn't exactly what you think it is, or is similar to an inverse trig function, but not quite. That are not quite like an inverse trig function, that you think maybe it's a hyperbolic function, inverse hyperbolic trig function. And that the integration of forms like these, you end up with these natural logarithms. You can, if you recognize this as inverse hyperbolic sine or inverse hyperbolic cosine, that's good. You can use, and we'll do an example, you can use trig sub to come up with this logarithmic form. So if you recognize this immediately as inverse hyperbolic sine, you're good. Now if you need to evaluate it, you have to remember that, or you have to figure out that this expression is what inverse hyperbolic sine is. But just gives you another little tool that you have at least some familiarity. Any questions on this? All right, I want to do, I have a couple of examples that I wanted to talk about. Let's look at an integral. Let's evaluate an integral, and then I wanted to do a derivation of a kind of an application of the inverse hyperbolic trig function. So let's find my integral that we're going to look at. So this is similar to something you might see on your homework or on a quiz or a test to evaluate this integral. So we want to evaluate the integral of 2 over x square root of 1 plus 4x squared dx. So we can do a couple of things here. If we look back at our integral forms for inverse hyperbolic trig functions, which one does this look like? Looks like our third formula, right? This looks like our third formula. And what are our u's and our a's here? U equals 2x, and du is going to be 2 dx, and a is one. A is just 1. So we can, if we recognize this form, we can plug this in, and we see that we have, I'm just going to write everything in. We have the integral of du over u over 2 square root of 1 plus u squared. So this is what we're looking at. I'm just plugging in everything that we have. I'll rewrite this as 2 integral du, and this will look exactly like what we want. 1 plus u squared. And we're set. And I just use my formula, and this is minus 2 natural log 1 plus the square root of 1 plus 4x squared all over the absolute value of 2x. All right. First question: where did the negative come from? Let's see. Yeah, our form, doesn't our form have, isn't our formula negative A?
No, the two's not. Yeah, it's negative 2, so it's negative 1.
Right. So I have a 2 in the denominator of the denominator, and that brings it up to the numerator. So I think we're good. We have a minus sign in our integration formula, and so I think we're set. Is everybody good? And the other, we could. This is also the inverse hyperbolic cosecant of 2x. But to evaluate it, we need this. We need it in this form. Now, the other thing to keep in mind, if you don't remember this, if you don't remember this formula, you can get here by trig substitution. So if I draw my triangle, I can get to the same place by trig sub. I'm not going to go through the whole thing. We can use trig sub on this form. This form does work for trig sub. So if I draw my triangle here, and this is theta, and I find it kind of interesting that we're doing trig sub for an inverse hyperbolic trig function. So it's kind of like double trig. I drew my triangle like this. This is 2. This is, sorry, I was looking at a different example. This is a 2. This is the square root of 1 plus 4x squared. This is 2x, and this is 1. So I get my substitutions. Cosine theta is 1 over square root of 1 plus 4x squared. Tangent theta is 2x over 1. I'm just writing down all the different relationships. Cotangent theta is 1 over 2x. I used this one to find x, so x is 1/2 tangent theta, and dx, I need my dx for my substitution, is 1/2 secant squared theta d theta. Often when I do trig substitution, I end up writing down more stuff than I really need, just in case. And we end up with the integral of, when we do all of our substitutions, it turns into the integral of 2 integral of cosecant theta d theta. And this gives us, this one's a hard one to remember. I think this is one that Ms. Hines said she told you just had to memorize. Natural log of cosecant theta plus cotangent theta plus c. And when we do our substitution, when we do our back substitution for theta, cosecant theta, cotangent theta, we end up with exactly this form with some simplification. Take some algebra to make it look exactly like this, but this leads us to the exact same place. Trig sub will lead us to the exact same place. Yes? No, you can go ahead. You have to wait. I'm joking. All right, are we good with the integration example? All right, let's. Yes.
We won't have to practice how to use trig sub to get trig sub.
Right, unless the problem says use trig substitution to evaluate this integral. If you had this on your note card, if you had your integration formula and you could make this substitution and get to right to here, beautiful. And a lot of times if it's tricky, I might say evaluate this integral. Hint, do not use trig substitution. That would be a hint that you might want to do something else that we've learned. So I try not to make it just like a cold, you have to know this off the top of your head. All right, so what I want to do, I'm going to do a derivation for an application, but I want to stop for a little bit because I know I've been talking for a long time. So let's take a quick break.
Or candy?
More candy.
What guy? Okay, Monica.
I don't own like any clothes that I can wear.
I'll just like those in like suits. Oh, that don't have any like. I'll go find some. Oh, being the president.
Recording. All right. So, our picture, and I mentioned the other day that a hanging cable is described by hyperbolic functions. The derivations are somewhat similar, but so I just want to go through this one example. It's kind of nice. So here's our setup. We have our axes, and we have a point here. This is P, and we have some point over here, and here's our curve, and I'm going to explain what we're talking about. And this needs to go, curve needs to go down and connect to that axis, like so. And this is at the point A0. This is X and this is Y. And what's going on here is that point P is pulling whatever our object is here that's moving along this curve with a rigid connector. So P starts at 0, 0. And pulls the point XY with a rigid connector of length A. Rigid. So the point starts here at 0, 0. The rigid connector is length A. I know my connector here looks shorter than here, so you just have to take my word for it that this length is A. This is also length A. So we start here at A0, and the point moves, P moves directly up the y-axis. And we want to come up with an equation for this curve that the point moves along. So what kind of situation, can you think of any situation that this would describe, where we're pulling, P is pulling directly along the y-axis with some kind of connector, it moves directly along the y-axis and is pulling this thing along. Anybody think of something that would be like that? I think, first thing I think of is like, so this is a dock, and your boat is out here in the water, and you're pulling the boat in from out in the water by walking directly along the dock. So you're connected to the boat by a rope, and we're assuming the rope doesn't bend. It's short enough that it stays straight. And you're walking directly along the dock, and you're pulling the boat to come into the dock, and the boat kind of swings along and eventually comes alongside the dock. And so the curve that boat would describe is this function. The second one that I think of is like a big semi, a tractor trailer going around a corner. So the front of the truck here is pulling this way, but the back of the trailer is back here on the other road. So as the tractor trailer pulls this way, the back of the trailer is going to track along some curve as the trailer pulls, or as the tractor pulls along the perpendicular road. So we want to come up with a formula for this curve. So we're going to say a couple of things. So at any moment the point is moving only in the direction of the connector. That's the force that's pulling on this point. So it's moving in the direction of the connector. So the connector is going to be in the direction of the tangent line to the curve. So the point is moving in the direction of the connector. So that's the tangent. That's going to be the tangent line to the curve. And the tangent line is also given by the derivative at this point. So we have we'll be able to come up with two expressions for the tangent line. We can figure out the slope of the tangent line and equate that to the derivative of the function. So here at the point where they're connected, I'm going to draw in another segment here. I'll draw it in a dotted line. So if I go over here, whoops. This distance is x, the point here, and this length on this side of the triangle is the square root of a squared minus x squared. So the slope of this segment, the slope here of the connector is, and I'm going to write minus because we're with my coordinate system, the slope is negative, minus the square root of a squared minus x squared over x. That's the slope here. And that equals the derivative of the function at that point. That equals dy dx. So the slope is the derivative of the function at that point. So this is a separable differential equation. Separable means we can get all the x's on one side and all the y's on the other side. So this is separable. So I can say that dy equals minus the square root of a squared minus x squared over x dx. And I integrate both sides. So y equals the integral of minus square root of a squared minus x squared over x dx. I need to, in order to integrate this, I need to use a trig substitution. The trig substitution that I did on this, I have an entire page. I tend to do a lot of steps when I do these. But what you come out with, if you want to see the work, we can go over the work, the trig substitute to do this. What we come out with is y equals a inverse hyperbolic secant of x over a minus the square root of a squared minus x squared. plus a constant. So if you had to do this integral, I would say that your book has tables of integrals. We'll talk about using tables a little later in the unit. Use tables. If you have an 89, your 89 would do this. Wolfram Alpha might help you out. Or you can do trig sub. The trig sub is not hard. It's just there's a fair amount of work. So it turns out that the curve that this tractor trailer describes, or this boat describes as you're pulling it into the dock, tractor trailer, the back end of the tractor trailer as it goes around the corner, the curve called the tractrix, what the name of this curve is, the tractrix, is an inverse hyperbolic secant function. So that's one application of inverse hyperbolic functions that comes up from a pretty straightforward situation. And again, if you want to see the work for the trig sub, I'm happy to go over it. But I just don't want to do the entire thing. Questions on that? The derivation for the hanging chain, which is called a catenary, is similar. You think about the forces. You assume that the chain itself has some mass, and you make some assumptions about the forces on the chain, and it turns out to be a hyperbolic function as well, rather than a parabola. All right. Homework. We're on page 396. There you go.